In this video, we're going to revisit alpha, that preset level that we determined before we do a study. And we're going to talk about how alpha is related to type 1 error. So in revisiting alpha, alpha has two purposes. It sets the boundary for our critical region. It tells us what are the low probability areas in the normal curve. And it tells us the probability that we are making a type 1 error. So we might think to ourselves, I'm going to avoid a type 1 error, and so therefore I'm going to make my alpha very small. In other words, I'm making that critical region very small. And the truth is, the further out we set our critical boundaries, the harder it is to reach them. So we might just say, I'm going to be as rigorous as possible, and I'm going to set my alpha at 0.01. But in doing so, we then have made our critical region very, very small. And it makes it hard for us to then find a significant difference when maybe there is actually a significant difference there. So here is a graphic that might help you to picture this a little bit better. So this is an example of what two-tailed tests would look like at the 0.05, 0.01, or 0.001 level. And you can think of that as 5 out of 100, 1 out of 100, 1 out of 1,000, if it makes it easier to visualize. These are different critical regions that we can set as researchers. Now, the alpha at 0.05 is what you're typically going to see in psychological research. But we could set it at 0.01, we could set it at 0.001. So what's the effect of doing that? Well, let's take a look at the z-scores that are associated with each of the alpha levels. So for an alpha level at 0.05, the z-scores that set off the critical area, the critical region, the low probability regions, are plus or minus 1.96. But if I set my alpha level at 0.01, that means that my sample mean is going to have to be greater than 2.58 or less than a negative 2.58 in order for there to be statistical significance. So it's a harder bar to jump over, a higher bar to jump over for sure. It does reduce the possibility of us making a type 1 error, but it also increases our type 2 error. We might be missing something. If something was significant at 0.05, it might not be significant at 0.01. It's a trade-off. And then finally at alpha 0.001, you can see the z-scores that serve as the critical boundaries are negative 3.3 and positive 3.3. So to obtain a z for our test statistic beyond that is going to be very, very, very unlikely. So yes, when we set our alpha at 0.001, we're really reducing that chance that we're accidentally rejecting the null when we shouldn't. But at the same time, we're making it really hard to find statistical significance as well. But having said all that, alpha equals 0.05 is typically the alpha level that will be set. So in our study, let's just take a look at that. The z was 3. So if we set our alpha before the study at 0.05, the critical boundary is plus or minus 1.96. And let's just say that we have our z-score again, but this time the alpha is 0.001. The critical boundary for 0.001 is plus or minus 3.3. So in the second case at 0.001, for a statistically significant result, a z-score greater than 3.30 is needed. So using 0.001 has reduced our type 1 error, our chance for type 1 error, but the critical boundary is harder to reach with our sample mean data. So this is the case where, depending on where the researcher had set the alpha beforehand, we may or may not have found statistical significance. If it was set at 0.05, our finding would be significant. If we preset our alpha at 0.001, our finding would not be significant. So it may seem, like I said, the best way around type 1 error is to make the alpha level as small as possible, but it's a trade-off. The smaller the alpha level will push the critical boundary farther in the distribution near the tail. And that means we need a larger treatment effect to reach the critical boundary. So let's do a learning check. From the scenarios below, which best describes the effect of changing from alpha of 0.05 to alpha of 0.01? Go ahead and pause the video to find the correct answer. Well, when we're changing from an alpha of 0.05 to an alpha of 0.01, we're decreasing the likelihood that we're going to reject the null hypothesis. Let's just take that part first. Because we've pushed out our critical z value further into tail, it's going to be harder to reject the null hypothesis. We're going to decrease the likelihood that we're going to be able to do that. And we're also at the same time decreasing the risk of type 1 error because, yes, by making it more stringent, we're going to lower the risk of making that mistake where we say there's an effect and there isn't. So those two things are happening. Okay, let's try one more. The results of a two-tailed hypothesis test produced a z of 2.75. Based on this result, what is the correct statistical decision? We've got 4 different options here. Let's take them one at a time. A, the researcher should reject the null hypothesis at 0.05, but not with alpha at 0.01. So you could use your unit normal table to figure out the z-scores at 0.05 and 0.01, but we already know that. At 0.05, it's plus or minus 1.96, and at 0.01, it's plus or minus 2.58. So we still would be rejecting the null hypothesis at 2.58, so A is not the correct answer. For B, the researcher should reject the null hypothesis with either 0.05 or 0.01. So let's think about that. Again, alpha at 0.05 is 1.96 plus or minus, and alpha at 0.01 is plus or minus 2.58, and we have 2.75, which is more extreme than either of those. So that is the case that the researcher would reject the null hypothesis with either of those. So the researcher would reject with either alpha of 0.05 or alpha of 0.01. All right, in our next video, we're going to talk about something called effect size. We've been talking about statistical significance, but that's only part of the story. Effect size is the next part of the story. I'll see you at the next video.